So far, we examined contaminants that could come from water and acids that the labs generally use. The other major source of contamination in a lab are the pipettes and the general labware. As a good laboratory practice, pipettes have to be calibrated as well as thoroughly cleaned. Cleaning procedures should ensure that the pipettes are free of contaminants even at PPT levels. Usually, pipettes have memory effect. Remnants of what you pipetted before will show up in later use even after thorough cleaning. Hence, the process of cleaning is very critical. In order to demonstrate the effect of manual cleaning, we scanned a 2% high pure nitric acid for impurities after delivering it through a thoroughly but manually cleaned pipette. The ICP-MS results in microgram per liter are shown in this table. As you can see, silver, aluminum, calcium, iron, sodium, and lead are very high. Very frustrated by the remnant contamination in pipettes, even after a thorough cleaning, our chemists designed a unique pipette washer. Here, rows of conical-shaped plastic pipette holders are connected to a water line. Water fills each pipette, shoots out of the pipette tip, and rains a shower of water over the outside of the pipette. Because water gushes out in force, it washes away all the impurities sticking to the walls of the pipette. Pipette washer has unique features. It can hold 23 pipettes, can accommodate 0.5 ml to 200 ml pipettes. It's a very small footprint to fit most spaces. It can also be used to dry pipettes after washing it by connecting it to a vacuum line. You can also enhance your washing by adding wash solutions or surfactants. So, once again we analyzed 2% high pure nitric acid solution delivered through pipettes that are washed in pipette washer. Most of the impurities were less than 0.01 ppb concentration, except for iron and calcium, which were at 0.2 ppb. This slide shows a comparison of impurities from the two processes, manual cleaning versus pipette washer. As you can see, calcium is about 18.8 in manually cleaned pipette, whereas from the pipette washer, it had only 0.20 ppb. Sodium was 19.1 in manually cleaned pipette, whereas in pipette washer it was less than 0.01. In general, the manually washed pipettes contain high pure impurities. This could be due to a number of reasons. When manually washing, you may tell your technicians to wash according to a lab protocol, but repetitive washing is prone to errors and also missteps. Pipette washer washes more effectively, thus cleaning the pipette inside and outside. So far, we have reviewed few things that are commonly used in the lab. Next to be considered are bottles. Calibration standards are shipped to you in bottles. You store diluted solutions in bottles. Bottles are of various types. Trace impurities from the walls of the bottles can leach into the solution and increase contaminants. The quantity depends on the type of material used for making the bottles. The ideal storage containers would be fluoropolymers, which is a Teflon, and synthetic quartz, polyethylene, and natural quartz. Borosilicate glass leaches out boron and silicon and is not suitable for trace metal analysis. This chart gives you an idea of contribution of trace impurities from different containers. Polystyrene, which gives you the major impurities like sodium, titanium, and aluminum. Total number of elements that were imported were 8 to a total concentration of 4 ppb. But polystyrene tends to become brittle in the presence of acids over a period of time. Teflon gives you about 19 total parts per billion in concentration of the major impurities calcium, lead, iron, and copper. Total number of elements may be 24, but it's expensive and not cost effective. Hence, the ideal storage container in this situation is LDPE, low density polyethylene. This gives about 23 total concentration of the ions, and the number of elements being 18. The major impurities are calcium, titanium, and zinc. But due to low cost, relatively low level of impurities, and is also more tolerant to acid, LDPE becomes the ideal storage container of choice. Tubing is perhaps not something you use often in your laboratory, but as a CRM manufacturer, we exercise a lot of care in the selection of tubing for packaging solutions. Sometimes we resort to manual filling to avoid contamination, even if it is labor intensive. If we had to choose a tubing amongst silicone, neoprene, and form ed, we use the form ed tubing because that is the least that imports least contamination in 5% nitric acid solution. Next to be considered is a sample preparation method. This is one of the most crucial steps. Samples can be digested in traditional open vessel or microwave oven. We must avoid, at any cost, sample-to-sample cross-contamination and be scrupulously clean with regard to anything that comes into contact with the sample. This brings us to the environment in which a sample is prepared and analyzed. So the first question you might ask, is my laboratory clean? To demonstrate, we concentrated redistilled nitric acid in regular and clean labs, and then we analyzed it. I want to explain what I mean by regular lab or a clean lab. Regular lab is what you encounter every day. It follows GLP protocols, maintains good housekeeping, and is kept spotless. Regular lab is a clean lab in an ordinary sense of the word. However, in this context, clean lab is one that is constructed with high quality special materials, has special air handling systems. I'll be explaining about this in a bit. But as you can see, the contamination from aluminum, calcium, iron, sodium, and zinc from regular lab are much higher than from clean lab. So in the previous slide, I mentioned about clean lab. What is a clean room or a clean lab? A room which has a gentle shower of highly filtered air for the purpose of transporting airborne particulate contaminants away from the sensitive samples and maintain a clean environment with low particle concentrations. Environment pollutants that are to be considered are dust, airborne microbes, aerosol particles, and chemical vapors. Applicable standards for this are ISO 14644 and the US Federal Standard 209E. The US Department of Commerce has discontinued the FS 209E. However, it is still widely used by the industry. As per my definition earlier, a typical clean room will have a controlled level of contamination that is specified by number of particles per cubic feet or cubic meter for a specified particle size.